The various techniques to optimize the deep neural networks. In the previous lectures, we have started the understanding of a multi-layer perceptron. So there are different ways in which we can optimize the learning of our deep learning models. And the contents we are going to cover today are limits of the shallow neural networks and why we move to deep neural networks. What are the limitations that lead us from shallow neural networks? So in the shallow neural networks, such as your multi-layer perceptron, where we have only input layer, one or two hidden layers, and then we have the output layer. So that is our basic understanding of a shallow network, where we have only one or two hidden layers. However, if we increase the number of hidden layers, we will call that a deep neural networks. So more than two layers, then we can call a network as a deep neural network. It can be categorized in that deep neural networks. So what are different types of activation functions? And we have to choose among different activation functions depending on our application and our training of our model. Then the importance of good initialization and what is dropout and bad normalization. So what are the limitations of shallow neural networks? So we studied the shallow neural networks where we have the input and we designed our network to get our output, and this was our hidden layer. So in the forward pass, we put the input, gave the input to our neural network over here, x1, x2, for example, x3, and the output over here is sent to your hidden layer, and we have output over here. Here we have our weight vectors, and also we have weight vectors j, k, ij. So this we can represent as a weight matrix also when we are designing a network, and all the weights in this region between the hidden layer and the first layer, the input layer, we can call them a weight matrix ij. When the forward pass or data is input into the first layer through the hidden layer, and then we have the estimation at the output. And each of these nodes, they have two components. First is your summation part, and the next is your activation. So this is your activation function, which transforms your with classifier in which we studied before. That was the classifier. So one of the classifier was sigmoid function that we studied. We can use sigmoid, we can use softmax classifier, ReLU classifier, or the activation functions. And sum is basically just the weight transpose multiplied by your x, and if it's your hidden node, then it is represented in this format. So we have two parts, each node, within each node. First is the summation part, and the second is your activation part. And the next thing that we studied was back propagation. And why do we need the back propagation? To update the weight values. So for back propagation, we are going to update the weight values using back propagation. And each back propagation we studied that we have to take the derivative, the partial with respect to the weight values, jk, and for this we take the partial with respect to jij. This is what we studied in the previous lectures. So this is a form of a fully connected network. And what do we mean by a fully connected network? That all nodes are connected by links. So these are your links, and each link has a weight value, and all of these weight values are represented by your weight matrix. And we have to take, for the back propagation, we will have to take our partial or derivative with respect to the weight values. And for the next layer again, we will have to take one more partial, and we call it the gradients. We have to update the gradients. So why do we need to update the gradient values? So we can update the weights. So if we have a weight t plus 1, we have a weight t. So this is what we are trying to do. We take the partial with respect to the weight, multiply it with your learning rate eta. This is your learning rate, and then subtract from the original weight value to get your updated weight value. So this part I was telling you that we have to take the derivative over here to update the weight, and then for here again we will have to take the derivative with respect to the weights here. So this was the back propagation algorithm. What are the limitations of neural networks? Shallow network versus your deep networks. So theoretically, we have studied that our shallow network can mimic any functions, but the number of nodes can exponentially increase in a shallow network. So the input, you can give your input in this format in such a way that your first layer can have any number of nodes. So if you want to mimic a function like this, a quadratic polynomial, so in this case what do? We increase the number of nodes. So we studied from AND OR operation we needed 2 nodes, and then hidden nodes, and for the XOR we needed 3 nodes. So we increase the number of nodes depending on our function that we are trying to mimic. So for this one, what do we need? How many nodes we will need? We have to design a network. So a simple NOT operation, it requires 1 node, right? So we can design our algorithm, we can mimic any function. Theoretically it is possible, but that increases as the function becomes more complex. We need more nodes in the first layer. So in order to avoid the exponential explosion, we have come up with a information that we can adopt the deep networks instead, that you use first layer with exponential number of neurons. What you can do is we can have many layers. Each layer will perform one function, right? So deep networks have a very strong power, but there are some problems. So we can restructure our problem or network model in this format from the shallow network to our deep network. So we increase the number of hidden layers, but we keep the number of neurons smaller in each layer. That is the target. So what are the advantages or disadvantages, pros and cons of deep networks? That deep networks have a power that you can solve very complex problem. However, they are hard to optimize. They are prone to overfitting, and there is a problem of internal covariate shift. So why and why this occurs, and what are the solutions? What are some of the solutions we are going to study in this lecture? So when I say that they are hard to optimize, what do we mean by that? So this is your deep network. We have many hidden layers. So for example, our classifier is a sigmoid classifier, and its value is, for example, less than 0.05. So when we take the derivative, the value is this. And we know that the partial of our weight value comes out to be this equation. ONK, 1 minus ONK. This is your target. This is the actual output. And we have a H and J, which is your output from the hidden node. And for the next layer, when we come here at this part, we will again have, between the hidden layers, we will have H1 minus H. And then if we consider multiple nodes, K is 1 to M. If we consider multiple values for input of Xn, I, this is our equation that we estimated in the previous lecture. Essentially what we are doing is we are updating the gradient. First you need to find this, next you need to find this, and here at this point you again need to find the weight values, update using your partials. So in this particular example that is given here, we have like 4 multiplication of our sigmoid function. So 4 times, if we start off with this and then we update it 4 times, 4 multiplications, so it becomes maybe less than 0.05. So the update to our model, and what do we mean by update to our model? Meaning thereby the weight updates on these links, it becomes very small, because the partial here will have an impact on all the nodes in the network, and partial that we will estimate here on the back propagation, it will affect all the nodes. So the weight update becomes very small. And the problem that we call this problem the vanishing gradient problem. The weight updates become so small that the model is not able to learn that quickly. Because of vanishing gradient problem. And why does it occur? Because if we have multiple layers in the back propagation process, we have to update the weight values in each layer using back propagation. That involves taking the partial with respect to your weight values on each layer. Here we have h and j, and then it is again multiplied here. So in the next layer it will again be multiplied and the process will go on. So we'll have 4 multiplications by the time we reach the input node. What are some of the limitations of neural networks? We discussed the overfitting, underfitting, generalization, and cross-validation in the previous lectures. And we studied overfitting. And we can call overfitting as a modeling error. When a model learns the training data all too well, such that the performance on the test data or the unknown samples degrades. So the performance degrades on the unknown samples because the model is trained too well on your given data. That's the problem of overfitting. So we need to find a general model to address the problem of overfitting. So if in this example that is shown here in this graph, we have our training error on your y-axis and model complexity on our x-axis. So if the model complexity is too high, our training error, of course, will reduce too much. That can lead to overfitting of our model. So our model will learn each and every data point, its location, even it will learn the outliers or noise in our data, which leads to an overfit model. So we have our actual model represented by this purple line, and then we have the model that we have calculated. So if the actual model is overfit, it is unable to find or predict the unknown data. And if our model is underfit, like this line, which does not fit this data, the actual samples that we have, then our model is not able to learn or predict, model is not able to predict the output for unknown samples accurately. So this model will not be a good model. So in this case, we can see not only the model, the actual model, and the model that the learned model, that is the purple line, and the actual model, they overlap, so we have a good prediction for the samples. So this is the actual model, the actual function that we have, that we are trying to mimic. Purple is the learned model, overfit model here, and in this case this is the underfit model, and the actual function is basically a sinusoid. So here when we write this true function, it is actually a sinusoidal, and or underfit or overfit model, the purple one, will not be able to predict the unknown samples. What do we mean by that? So this is our purple is our learned model. So if we want to find a point over here, then this purple model that we have here, it can predict the values with very small error, and that is the target. So overfitting is not suitable for deep networks, and we have to address the problem. And then we have the issue of internal covariate shift. So internal covariate shift occurs when there is a change to the input distribution for a network. So if the input distribution of a network changes, the hidden layers, they try to learn the or adapt. Hidden layer adapts to the changes. Due to the new distribution. And this slows down the training process, because the model has to retrain because of the new distribution that we have. And what is the problem with the internal covariate shift? It leads to a longer time to converge to a global minimum. So that is the problem. So if there is a change, like in this example, this was your actual distribution, and here we have on the right hand side a shift in the actual distribution. Now the model has to relearn this new pattern, and it slows down the training process. And when the model training is slowed, it takes a longer time to converge to a global minimum, which is not desirable in training or networks. So some of the limitations of the neural networks and what can be the solutions. When we have the high model complexity, what we can do is we can convert the model into simpler structures with more hidden layer, but the simple number of layers should be increased, number of layers, and the actual structure of each layer should be simplified. When the model is hard to optimize, we need to decide or choose good starting points. So there are different techniques that we can use to decide or determine the starting point or the initialization of model weights. So now I will use weight matrices. So between each layer, in terms of programming, we would have weight matrices. Or you could do is you could change your activation function depending on your training results and use the mini batch gradient descent, where we mean that we give multiple inputs, estimate the loss, take the average of the loss, and then update the weight values per batch. So we first give 60 samples, estimate the loss, update, take the derivative for the backpropagation, and then take the average and then update the weight. Instead of updating the weights for each sample separately, update the weights after certain number of predetermined number of samples, or the mini batch. So when we combine or give the input x1, x2 up to xn, n is 60, that means the batch size is 60, so this is your batch 1. So after this, you update your weight update. Rather than weight update for each individual sample input, update after a batch. And then we have the problem of overfitting. So we need to have a larger size data. We should increase the data size that we have, and we can use some regularization methods to address the problem of overfitting. And another problem that we have is the internal covariate shift and how we can address batch normalization. So for each batch, you present your data with the same representation. You convert your data representation into this format for batch 1, then for batch 2 again, normalize your data, and then put it into the training network. There are different structures of deep networks. What we have studied in the previous lecture was fully connected deep networks, where all nodes are connected with all the other nodes in the next or the previous layers using links, and those links have weight values. So it has high structural complexity because we have connection from each node to the next node, and it can be applicable to any data types. And examples of these structures are deep belief networks, stacked autoencoders. Then we also have some partial connected deep networks. So not all nodes are connected to the nodes in the previous or the next layers. So it reduces the complexity to special data types. And we can address the spatial or temporal sequential data. We will discuss that later. So some of the networks are convolutional neural networks, recurrent neural networks, and recursive neural networks. So we will address them, 2 of these, in our lecture content.